Commissioning a power transformer is a multi-dimensional verification process. Before a unit joins the electrical grid, engineers must prove the integrity of its dielectric insulation, its magnetic core, its internal electrical continuity, and its dynamic control systems. But before a single test lead is connected, the operation demands an absolute zero-energy safety baseline. This means strict physical isolation, verified grounding, and barricaded lockout-tagout boundaries around the entire asset. We do this because the objective is to validate the factory design against the field reality. A transformer may pass every inspection on the assembly line, but transit vibrations, moisture ingress, and installation handling can compromise its internal geometry. Part of establishing that baseline is physical preparation. Every bushing must be thoroughly wiped down to remove dust, moisture, and conductive contamination. If left on the ceramic or polymer surfaces, this residue creates a path to ground that will cause flashovers during 5 and 10 kilovolt testing. That pristine, mathematically verified as found safety state is the only valid starting point. Any data collected from a compromised setup is useless for subsequent diagnostics. Generating that data requires highly specialized instrumentation. To stress the insulation boundaries, technicians deploy high-voltage DC and AC testers, most notably the 5 kV Megger and the 10 kV Doble test set. To evaluate the internal windings and core, they use low-resistance microohmmeters and frequency response analyzers, capable of detecting millimeter-scale mechanical shifts inside the tank. Every measurement is evaluated against a strict regulatory hierarchy, referencing IEC, AAA, and NEMA standards. When project specifications, manufacturer guidelines, and international standards differ, the rule of governance is absolute. Apply the most stringent requirement. Because this data forms a permanent legal record, the instruments themselves must carry current calibration certificates. Every test sheet requires the traceable serial number of the exact device used to generate the reading. Environmental factors are also captured. Ambient temperature and relative humidity directly impact insulation resistance, so these variables must be recorded to normalize the raw data for accurate longitudinal comparison over the transformer's lifespan. Ultimately, commissioning serves as both an engineering proof and a legal certification. It relies entirely on high-precision instrumentation and unyielding adherence to international standards. The active sequence begins by verifying the dielectric health of the asset, starting with winding insulation resistance, or IR testing. We apply 5 kilovolts DC to the high voltage, low voltage, and tertiary windings. This document shows 6 connection diagrams isolating specific boundaries. We analyze this data by calculating the polarization index, the ratio of the 10-minute to the 1-minute resistance reading. A PI of 1.25 or greater proves the insulation aligns dipoles properly under sustained stress. This schematic highlights the procedure for core and frame insulation testing at 1 kV DC. Notice the explicit requirement. The links connecting the core and frame to earth must be physically removed to prevent a false ground reading. We inject the test voltage to verify that the core and the clamping frame are electrically isolated from the main tank. The acceptance criterion demands an insulation resistance exceeding 10 megohms. Next is the tan delta, or power factor test. This reference diagram illustrates the 10 kV AC injection into the bushing test loops. It also details the requirement to ground or guard any non-tested windings to accurately measure the charging current and dielectric losses. Tan delta testing identifies microscopic moisture and contamination inside the paper and oil. For a healthy oil-filled transformer, the measured power factor must remain strictly below the 0.5% limit. We then extract fluid for the oil dielectric breakdown test. The sample handling is precise. Technicians must avoid introducing air bubbles, ambient moisture, or particulate matter that would skew the dielectric strength readings. Inside the test cup, voltage ramps up across submerged electrodes until the oil literally arcs over. We run multiple breakdowns to calculate the final average. Together, these tests prove the dielectric container is physically sound and ready to manage high-voltage stress without internal tracking, arcing, or failure. Moving inside the tank, this schematic outlines winding resistance testing. We use Kelvin leads on primary and secondary connections to eliminate test lead resistance errors, recording measurements across all sequential tap changer positions. Because copper and aluminum resistance changes with heat, we apply a specific temperature correction formula. normalizing all field readings to a standard reference of 75 degrees Celsius for accurate factory comparison. This testing diagram details excitation-current testing, which verifies core symmetry. We apply a 10 kilovolt injection on the high voltage side, while keeping the low voltage side entirely open circuit to detect no load core faults or shorted turns. This manual page shows the setup for the transformer turns ratio, or TTR test, mapping the connections across the 3-winding bushings. The goal is to verify phase angles and ensure the measured voltage ratio deviates no more than 5% from the nameplate rating. These schematics demonstrate vector group testing. By applying specific phase shorting connections and solving the corresponding voltage equality equations, we confirm the physical terminal identification and the correct phase displacement clock number. This reference details magnetic balance testing. When we inject a low-voltage AC signal into one phase, it induces predictable voltages on the remaining two. The sum of the two induced voltages must equal the injected voltage, confirming the core's magnetic path is intact. This sequence of low-voltage diagnostics yields a complete DNA profile of the transformer's internal physical assembly, proving the coils and steel laminations are exactly where they belong. This illustration covers the short-circuit impedance test. Notice the instruction requiring the low-voltage windings to be shorted with massive current-rated links. We then apply a 3-phase injection on the high-voltage side and measure the resulting current against the average voltage. We derive the percentage impedance by dividing the measured impedance voltage required to drive full load current by the rated tap voltage. Under SEC standards, the calculated field impedance must remain within a strict plus or minus 10% deviation from the factory nameplate value. This diagram shows zero-sequence impedance testing. Here, the phase terminals are linked together, and a single phase voltage is injected against the neutral to calculate the zero-sequence percentage. This exact value is critical for system planners. It directly dictates the earth fault coordination and determines how the neutral grounding protection will behave during a line-to-ground short circuit. By empirically determining these impedance values, we ensure the actual hardware behaves exactly as predicted by the utility network's digital fault flow models. This schematic references frequency response analysis. Using the specified end-to-end open and short circuit measurement methods, we send a frequency sweep through the windings to establish a baseline signature for detecting core or coil movement. Because high-frequency signals are highly sensitive to stray capacitance, test lead routing and grounding lengths must be perfectly repeatable to avoid generating false diagnostic signatures. Moving to dynamic systems, this testing manual outlines on-load tap changer checks. We measure the motor's starting and running current consumption for every tap transition and verify mechanical direction using the rotation check arrows. We also perform a deliberate one-phase removed check, simulating a supply loss to verify that the motor drive protection relays correctly block operation and trigger alarms. This control panel diagram details the cooling fan motor testing. Technicians measure insulation resistance directly through the terminal blocks, verify correct airflow rotation, and log phase data into the starting current consumption table. This illustration shows temperature sensor calibration. We place the sensing bulbs into a controlled immersion oil bath, verifying that the local gauges read within 3 degrees Celsius of the reference standard. For the winding temperature indicators, we use secondary current injection into the heater coils, simulating the internal heat rise generated by load current to verify precise trip thresholds. This reference table maps the supervision functional checks. Technicians manually actuate the book holes relay, pressure relief devices, and oil level floats to ensure each contact matches the designated function matrix. We follow the signal path all the way to the control room, verifying the trip commands through the human-machine interface to guarantee correct mapping to the substation gateway. These functional checks provide the final layer of assurance, proving the transformer's heavy copper and steel structures are actively guarded by highly responsive protection systems. When data deviates from the standard, the energization sequence stops. If the polarization index falls below 1.25, it indicates severe moisture or contamination, requiring immediate oil processing or bushing remediation. If magnetic balance patterns are asymmetrical, or turns ratio deviations exceed 0.5%, the test has identified a severe physical defect, usually transit damage, collapsed coils, or inter-turn short circuits. Anomalous impedance data suggests either an error in the system fault studies or an internal displacement of the windings, which would compromise the unit's ability to survive a through fault. Analytical, we verify this mechanical stability by comparing field FRA traces directly against the factory baselines. Frequency shifts in the mid-band ranges act as clear indicators of radial deformation or winding displacement. For dynamic systems like the on-load tap changer, a motor drive failure or abnormal current signature initiates a troubleshooting path focused on mechanical binding in the diverter switch or logic errors in the contactors. These data anomalies represent the final opportunity to detect a defect before it manifests as a catastrophic multi-million-dollar failure on the live grid. Because of the massive capacitance involved, every high-voltage test requires a mandatory hold point. A witness must visually confirm the safe, complete discharge of stored energy before leads are moved. Once testing concludes, the as-left restoration protocol begins. The core and frame ground links that were removed for 1 kV testing must be bolted back into their original documented positions. The commissioning team must then physically walk the perimeter, executing a visual verification to guarantee all heavy temporary shorting links and test jumpers are entirely removed from the bushings. Inside the marshalling kiosk, every temporary override, forced sensor signal, and protection trip block used during functional testing must be cleared and rearmed. Grave. If a technician forgets to reinstall the core earth link, the massive steel core remains ungrounded. Upon energization, it will charge like a capacitor until a violent electrical arc tears through the insulating oil to reach the grounded outer tank. Only when the site witness confirms full physical restoration, complete isolation, and 0 standing alarms on the control board is the asset finally released for its first live voltage grid synchronization.